Alright, we're going to talk about escape speed and derive the relationship for it, and then work out a couple examples to get comfortable with the calculations. The basic idea of escape speed is I have some gravitating object, so say it's a planet with a mass capital M, a radius capital R, and I have some little object with a mass little m sitting on its surface. It doesn't have to be set up this way. You could have calculate what's the escape speed from Jupiter's orbit to get away from the sun. But for right now, we're just going to think about having this little mass m sitting on the surface of the planet. The basic idea with escape speed is how much kinetic energy does this little mass m have to get infinitely far away from this gravitating object. And basically you can think of that as how fast does the mass little m have to be moving such that it can overcome the force of gravity from this planet. To derive this, I'm going to do a couple relationships. We're going to talk about kinetic energy that this mass little m has, and that is a half its inertial mass times its speed squared, and then how much gravitational potential energy it has. And that is minus universal constant of gravitation, big G, mass of the planet, this test mass m, and the distance that separates them initially, which is the radius of the planet. And if the object is moving at its escape speed, then the total energy, which is kinetic plus gravitational, is 0. So at the escape speed, half m v escape squared minus g big M little m over r equals 0. So if it's moving at faster than the escape speed, the total energy will be positive. If it's moving slower than the escape speed, the total energy would be negative. And at the escape speed, the total energy will equal 0. Okay, we want to solve that equation for the escape speed. And I can get rid of little m. Its value is arbitrary because it's in both terms, so it cancels out. Because it would have basically more inertia contributing more to the kinetic energy and more gravitational mass contributing more to the gravitational potential energy. And those two have to precisely cancel out. So I want to solve for v escape, get it by itself. So I'm going to take this term and move it to the other side. I have a half v escape squared equal to constant of gravitation, mass of the planet over the radius of the planet. I need to multiply both sides of the equation by 2. So we'll have v escape squared is 2 gm over r, and we clear the square by taking the square root of both sides. So v escape is 2 gm over r, all square root. So that's how we calculate the escape speed. Now let's do a couple examples. I'm going to take that relationship that we just developed, and first example, let's apply it to the Earth. And let's get our constants that we're going to need. So big G, Newton's constant of universal gravitation, is always the same. 6.67 times 10 to the minus 11. And it is that value when we're in our meters, kilograms, seconds set of units. So it's meters cubed per kilogram per second squared. We need to know the mass of the Earth is, which is 5.97 times 10 to the 24th kilogram. And we need to know what the radius of the Earth is, 6.38 times 10 to the 6th meters. So the average radius of the Earth. All right, and since G is in this set of units, I know the mass has to be in kilograms and the radius has to be in meters. If it's not, then it's not going to work out. We're going to have some additional factor from converting one set of units into another. All right, so we put this all in and calculate the escape for Earth. I'm going to have a 2, 6.67 times 10 to the minus 11. And it's meters cubed over kilogram second squared. I'm going to have the mass of the Earth, 5.97 times 10 to the 24th kilograms, because Earth is kind of big. And then we're starting off on the surface of the Earth, so R is the radius of the Earth, 6.38 times 10 to the 6th meters. And this is all under the radical for the square root. All right, so let's look at the units for just a second. The kilogram is going to cancel out with the kilogram, which is good, because I know speed can't have kilograms in it. And the meter in the denominator is going to cancel out 1 power of the meter. So this is going to work out to be some number I'm going to take the square root of, and it has units of meters squared per second squared. Once I take the square root, that'll be in meters per second, which is what we expect for a speed. So I check myself as I was going along, and at least my units are working out. You put that in your calculator, and I'm knowing everything to 3 digits, so I'll have the answer to 3 digits. 1.12 times 10 to the 4th meter per second, which is fine. But I'm going to also note that's 11.2 kilometers every second. So if you wanted to take your baseball and throw it fast enough that it would never fall back down to Earth, Earth's gravity would just continually to slow it over time until at an infinite distance away, it just then comes to rest. You would have to throw your baseball at 11.2 kilometers per second. If you are an astronomy fan, physics fan, the other thing to just note, since we're here, is that the escape speed is square root of 2 bigger than the speed you need to have for a circular orbit. Okay, so let's try another example. We'll look at our old friend, Churiguri. So we want to apply the same equation to comet 67P, which is Churyumov-Gerasimenko. Which was studied and even had a lander land on it from the European Space Agency. So for Churiguri, mass, Churyumov-Gerasimenko, is about 3.1 times 10 to the 12th kilogram, which you can measure from the motion of the spacecraft in orbit around it. And its radius sort of looks like a duck, so talking about sort of a rough estimate of what the radius is, because Churyumov-Gerasimenko looks very much like two comets that collided and stuck together. But think of that as like an approximate radius, or the radius of a radius that would correspond to a sphere that had the same volume as Churiguri, which is good enough for our estimate. So escape speed 2 times g. G does not change. 6.67 times 10 to the minus 11 meters cubed over kilogram second squared. Mass 3.1 times 10 to the 12th kilogram over 2 kilometers in meters, so 2.0 times 10 to the 3 meters. That's all under a radical. All right, so we go through and look at our units again. So we're trying to be careful and avoid mistakes. Kilogram is canceling out with kilogram again. Meter is going to cancel out with 1 power of meter, leaving me with meter squared per second squared, which will be a speed after take the square root. And you go through and calculate that, and you'll find the escape speed 0.45 meters per second, which that's an escape speed you can attain. A decent jump, you would have a speed greater than that, so you could jump off of comet Churyumov-Gerasimenko and never come back. It also made the landing of the Philae lander on Churiguri a little bit dicey. You have to be moving very slow relative to the comet and try not to bounce. And in fact, the Philae lander did bounce and wound up on its side. So you think of that very slow escape speed telling you that the force of gravity on Churiguri is very small.